All right, section 8.2, we talk about the difference between exponential growth and exponential decay. So you can see what I have written down so far is that both of these equations are a times b to the x power. That is their general form. For a growth function, a must be greater than 0 and b must be greater than 1. Okay, a is greater than 0 and b is greater than 1. So one example of that could be like f of x equals 2 times 4 to the x power. That would be a growth function because b is 4 and a is 2. For decay, a is greater than 0, and in this one, b is less than 1 and greater than 0. So for example, we could have f of x equals 3 times 1/2 to the x power. So b is 1/2. 1/2 is between 0 and 1. Okay, so that is the difference. The b value is between 0 and 1 for a decay, and it's greater than 1 for growth. So if we look at this, in the one on the left, we have 2 to the x power. For this one, if we write this down, a equals positive 1, b equals 2, h equals 0, and k also equals 0. So if we were to graph this, we should put 0 somewhere in the middle. That's our h value. So h should go somewhere in the middle. The domain is all real numbers. And as you know from section 1, that's true for every exponential function. The one on the right, a is also 1. For this one, b is 1/3. H is 0 and k is 0. Again, because it's minus 0 plus 0. That's where the h and the k come from. And h should go in the middle again, so 0, -1, +1, +2. Okay? The range for both of these is going to be y is greater than 0. And before we graph them, we'll talk about down here the asymptote. Since each of these has a k value of 0, that means for both of these, the asymptote is y equals 0. So our asymptote is going to be at y equals 0. So that blue line. So the one on the left, if you plug in -1, you would take 2 to the negative first power. That's 0.5. If you plug in 0, it'd be 2 to the 0 power, which is 1. When you plug in 1 and 2, you get 2 to the first, which is 2, and 2 to the second, which is 4. So if we graph this, -1, 0.5, 0, 1, 1, 2, and 2, 4, this is clearly going to be going up from left to right. And if you graph the one on the right, 1/3 of the negative first power is 3. 1/3 of the 0 power is 1. 1/3 of the first is 0.3, and 1/3 to the second is 0.11 repeated. So -1, 3, 0, 1, 1.3, and 2.1. So this will be down really steep and flatten out. So let's see if I can do this. Well, something like that. So clearly the one in the blue is coming down from left to right, and the one in the red is going up from left to right. And that is the difference in exponential growth versus exponential decay. So I'll put this is growth, and this one over here is decay. Red is growth, blue is decay. So if we slide down to example 2, okay, now in this one, a is -1, b equals 1/4. So we talked about this earlier, but if a is less than 0, so a is negative, it's not growth and it's not decay. H is 0, and in this one, k is 2. So the asymptote is y equals 2. The domain is always all reals. And in this one, since a is negative, the range will be y is less than 2. And again, remember, these two are always going to be the same number. One has an equal sign, and then one will have a less than or greater than. So I put the asymptote on here. The asymptote's at y equals 2. K should go in the, or H should go in the middle, so H is 0. So put 0 in the middle somewhere. When we type these in our calculator, I would type it in just as it looks there. Negative, let me zoom in. It should be negative parenthesis 1/4 to the negative first power plus 2. And you'll get negative 2. You'll get 1. You'll get 1.75. And this one's like 1.93. So when we graph them, negative 2, say negative 1, negative 2. Oops, I apologize. Negative 1, negative 2 is right here. 0, 1. 1, 1.75, and 2, 1.93. So this graph is going to go up really fast and then curve. Actually, I'm going to do this in a highlighter. Make it bigger. So there it is. So that's neither growth nor decay. Okay, the last part, we're just going to talk about the model. So a decay model will look like this. A times 1 minus r to the t power, where y is the current amount or the balance. A is the initial amount. R is the percent decrease. So to say it's like decreasing by 5%. 1 minus r is the decay factor. And t is the time in years. So it's just like the growth model we covered earlier in section 1, except for now it's a minus r instead of a plus r. So they tell us that there are 40 homes in your city, and each year 10% are expected to disconnect. So 10% disconnect from a septic system and connect to a sewer system. So the disconnect means they're going away. So that's a decrease of 10%. So R is 10%, which is 0.10. And A is going to be 40,000. So it says to write a general model. The general model will be y equals 40,000 times 1 minus 0.10 to the t power. Or you could put 40,000 times 0.9 to the t power. And then we want to estimate how many homes will be using a septic system after 5 years. So that means t is 5. So we take our model times 0.9 to the 5th power. So we would end up with about 23,620 homes. So after 5 years, we go from 40,000 to 23,620. Right, and that's how growth decay models work. They're going to go down really fast and then flatten out. So if we graphed it, it would look something like this. Down fast and then flatten out. That's what your decay model will look like. Right, and that's all we got for today. And I will see you guys in class.